Let us discuss this example. Okay, so in this example, we have a two matrix D1 and D2, which are defined on a non-empty set X. Okay, and we have two positive real numbers K1, K2, which will satisfy this condition. Okay, that is a very important thing. After that, we have to prove a sequence Xn in X is bounded in X D1 if and only if Xn is bounded in matrix space X D2. So this thing we have to prove. If and only if part is there, so we should assume one part first. We will try for the second part first. Okay. So I have written the given information. This information is so much important for us, and I have started with by assuming one information. So I have assumed Xn be a bounded sequence in matrix space X D1. So sequence is bounded, so therefore there exists a positive real number m. Okay, I will write that thing. So therefore there exists m belongs to R plus positive real number m such that d1 of xn xm less than or equal to m for all nm belongs to set of natural number. Okay, belongs to set of natural number. Okay, what will I do? So this is a bounded sequence, so that's why we could write it. After that, I will multiply both sides by k2. What will happen if I multiply both sides by k2? K2 d1 of xn xm, okay, less than or equal to k2 m. I multiply both sides by k2. K2 is also positive real number, so no need to worry. But see, from 1, d2 of xy is less than or equal to k2 of d1 xy. So that's why what can I write from 1? From 1 we will have d2 of xn xm less than or equal to k2 of d1 of xn xm, which is less than or equal to k2m. This is true for all nm belongs to set of natural number. Okay, so what we get here, a less than b, b less than c, so that's why a less than c. So therefore d2 of xn xm less than or equal to k2m. I will call it as m dash. So therefore d2 xn xm less than or equal to m dash for all nm belongs to set of natural number where our m dash is k2m, which is again a positive real number. Since k2 is positive, m is positive, so that's why product of these two is also positive. So therefore d2 of xn xm less than or equal to m dash, right? So this is a definition of bounded sequence. So therefore xn is bounded in X D2, since we have a matrix D2 this time. So we started with it is bounded in X D1, and we started with D1, and finally we proved D2 of X and Xm less than or equal to M dash. So therefore sequence Xn is bounded in a matrix space X D2. Okay, so after that we will discuss converse part of it. That means now we will assume Xn is bounded in X D2, and we will try to prove yes, Xn is bounded in matrix space X D1. Okay, so make a screenshot of it, then we will go further. So conversely, we assume sequence Xn is bounded in a matrix space X D2. So let us use definition of bounded sequence. So therefore, there exists a positive real number m such that what can we write? Such that it is bounded in X D2. No, so D2 of xn xm less than or equal to m for all nm belongs to set of natural number. So let us use equation 1 again. Okay, so I have removed that equation 1, but you can see here it is mentioned in that given question. So d2 of xy is greater than or equal to k1 of d1 of xy. So if I use this inequality here, what will I get? So therefore k1 of d1 of xn xm less than or equal to d2 of xn xm, which is less than or equal to m for all nm belongs to set of natural number. I should mention from 1. I should mention, okay, from 1. So see, a less than b, b less than c. So that's why a less than c. Let us write. So therefore k1 d1 of xn xm less than or equal to m for all nm belongs to set of natural number. K1 is a positive real number, so it is possible to divide both sides by K1. So let us divide both sides by K1. So therefore, we will have D1 of xn xm less than or equal to m by K1. Nm belongs to set of natural number. Getting, I will call it as m dash. So therefore, D1 of xn xm less than or equal to m dash for all nm belongs to set of natural number. I should mention what is m dash here, where m dash is equal to m upon k1. See, m is positive real number, k1 is also positive real number, so their ratio is also positive real number, so it belongs to r plus. So again we get a definition of bounded sequence. Okay, so this is bounded in what? X d1, since we have a matrix d1 here. So therefore sequence xn is bounded in matrix space x d1. So by assuming a bounded sequence in matrix space x d2, we proved that it is bounded in matrix space x d1. So converse part also we have done. Okay, thank you, bye bye.